You know that feeling, right? When you really want to get something, properly understand it, not just, skim the surface.
Yeah, like you're swimming in information, but actually thirsty for real insight.
Exactly. And that's why we're here. Welcome to the Deep Dive. We take your sources, your curiosity, and we dig in to find the gold.
And this time, you've given us quite the collection. Some really fascinating Russian language scientific texts. I saw the Popular Library of Chemical Elements in there. Ushta. Yeah, Ushta sounds great.
It does. And it looks like a really rich source. Seems to cover a whole range of elements, their properties, their stories.
It really does. It's a broad view of these fundamental, building blocks of everything around us. So we're set for a journey, I think, looking beyond just the periodic table basics.
Okay, so our mission today.
Okay.
Pull out the most interesting, the most impactful stuff about several key elements from these volumes. Give you, our listener, a clear, engaging grasp of what makes them tick and why they matter.
Precisely. We'll be hitting quite a few. Let's see. Cadmium, tin, lead, bismuth, cerium, gold, of course.
The classics, but also the workhorses, right?
Yep.
Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine.
Argon, neon, sodium, magnesium, aluminum, and even the heavy hitters like uranium, neptunium, and plutonium. Seems your sources had quite a bit to say on those.
Loads. Okay, let's jump in. First up, cadmium. Maybe a bit of an unsung hero in the metals world.
Could be. Cadmium, number 48 on the chart, atomic mass about 112.41. It actually has a kind of serendipitous discovery story.
Oh, do tell.
Well, it was found back in 1817 by a German pharmacist, Friedrich Strohmeyer. And the interesting part is he wasn't even looking for a new element. He stumbled upon it as an impurity while he was studying zinc oxide.
No way. Just like that. Finding something totally unexpected in what you thought you knew.
Exactly. And that's actually pretty typical for cadmium. It often hangs out with zinc in ores, which naturally made separating the two a real challenge back in the day. They're almost like mineral cousins, often found together, along with lead and copper sometimes too.
So it's a bit of a geological tag-along. But it definitely found its own uses, didn't it? I think preventing rust is a big one.
You're spot on there. One of cadmium's main gigs is anti-corrosion coatings, especially for steel. It's just incredibly resistant to atmospheric conditions.
You know that nasty stuff.
Yeah, even in tough industrial areas or salty marine environments, that makes it really valuable in things like shipbuilding and aircraft construction too. Places where materials just take a constant beating from the elements.
That makes total sense. You need that tough outer layer in those demanding spots. Sort of a metallic bodyguard. Now, here's something that really caught my eye. Its role in nuclear power.
Ah, yes, that's another really, really crucial application. Cadmium turns out to be fantastic at absorbing neutrons.
Neutrons, okay. The little particles flying around inside a reactor.
Exactly those. Think of them like tiny bullets pinging around. Cadmium can effectively catch or stop these bullets, which is absolutely essential for controlling the nuclear chain reaction.
So the control rods in reactors, they use cadmium.
They do. Cadmium control rods act sort of like the volume knob on the reactor. Operators use them to manage the rate of fission, turn it up or down.
The volume knob for atoms. I like that. That makes it really clear.
Right. And what's even more fascinating is that a specific version, an isotope of cadmium called cadmium-113, is particularly brilliant at capturing the thermal neutrons.
Thermal neutrons, meaning the slower ones.
The slower moving ones, yes. The ones most likely to cause more fission. And even though this cadmium-113 only makes up about, 12% or so of natural cadmium, it does a huge chunk of the neutron-absorbing work.
Wow. That's amazing. Such a small fraction having such a big impact. What does this cadmium get up to?
Well, you'll also find it in some alkaline batteries, the nickel-cadmium type, 9U lead. They were really common for rechargeable things for a long time.
Right, I remember those.
It's also used in certain types of solder for joining metals, and even as a component in some pigments, giving things bright yellows and reds, and also as stabilizers in some plastics.
So, quite versatile. From batteries to colors. But there's a catch with cadmium, isn't there? I feel like I remember hearing it's quite toxic.
That's a very important point, yes. Cadmium and its compounds are toxic. That means handling requires great care, and its use is definitely restricted in certain areas like food packaging to avoid contamination.
A good reminder that even useful elements can have a dark side if not managed properly.
Absolutely. Okay, let's shift gears. How about another metal, one with a really long history stretching way back to ancient times? Tin.
Tin. Element 50, sulfugacin. My first thought is always old tin cans, but I know the story is much bigger than that.
Much bigger. Tin's been valued for thousands of years, probably most famously as a key ingredient, alongside copper, in bronze. That alloy really changed ancient technology.
Oh, it's age right. Huge deal.
Huge. And the main source of tin is an ore called cassiterite. That's basically tin dioxide, SnO2.
Okay, so bronze shows its historical importance. But what makes tin itself useful?
Well, it has several key properties. It's pretty resistant to corrosion, which is a big one. It's also very malleable, easy to shape without breaking, and it has a relatively low melting point.
Cool melting point, easy to shape, doesn't rust easily. It sounds perfect for coatings.
Exactly. That's led to its use in tin plate, essentially steel sheets coated with a thin layer of tin. That's what those tin cans actually are. The tin protects the steel from rusting.
So it's like a protective skin. Makes sense for food preservation and things. And I know it's also vital in electronics, right? Solder.
Precisely. Tin is a fundamental component in solders. Those low-melting alloys are absolutely essential for joining metal parts together, whether it's tiny connections on a circuit board or pipes in plumbing. They make strong, reliable connections.
Got it. And it's not just the pure metal, is it? I remember reading about organotin compounds. That sounds complex.
They are interesting. Organotin compounds are where tin atoms are bonded directly to carbon atoms, and they have a surprisingly diverse range of uses.
Like what?
Well, some act as stabilizers for PVC plastic, making it more durable. Others are used as biocides, chemicals that control harmful organisms like fungi or insects. Some even find uses in veterinary medicine.
Wow, stabilizers, biocides. That's quite a spread. But I think I remember some issues there too. Environmental concerns.
That's correct. Some organotin compounds, particularly tributylin or TBT, which was used in anti-fouling paints for ships, have raised serious environmental concerns. They're toxic to marine life, and they persist in the environment for a long time.
Right. So another case where usefulness comes with responsibility.
It really highlights the need for careful research and regulation, doesn't it?
Definitely. Oh, one last thing on tin, its connection to printing. Historically.
Yes. Good point. Tin was important in the early days of printing presses. It was used in the alloys that made the metal type the individual letters. Tin helped make the type durable, but also easy to cast accurately.
Amazing how these elements just pop up in fields you wouldn't necessarily connect. Okay, moving on to another heavy hitter, literally and figuratively. Lead.
Lead, PB element number 82. It certainly has, as you say, some weight associated with it, both in density and its modern reputation.
Yeah, it has a pretty complex history.
It does. Lead's high density, its softness, its low melting point, these made it incredibly useful for centuries. But as we now understand the health risks much better, many traditional uses have declined sharply. Think lead in paints or plumbing pipes.
Thank goodness, right? Lead paint, lead pipes, major health hazards we're better off without. But lead hasn't totally disappeared, has it?
No, not at all. It's still absolutely vital in several key areas. Lead-acid batteries, the kind in most cars, still rely heavily on lead.
Right, car batteries.
And its sheer density makes it an excellent shield against radiation. So it's crucial in medical settings for X-ray protection and in nuclear facilities. Plus, it's still used in some specialized alloys where its specific properties are needed.
So, still doing some very important jobs. Where does most lead come from? What's the main ore?
The primary ore is galena. That's lead sulfide, PBS. It's actually quite a common mineral, which partly explains why lead was so widely used throughout history. It was relatively easy to get.
It's really striking how our view of an element can shift so dramatically, isn't it? From indispensable material to something handled with extreme caution.
It really is a lesson in evolving knowledge. Okay, speaking of heavy metals, let's touch on bismuth.
Bismuth, B, number 83, right next door to lead.
It is. Another heavy metal, but with some different characteristics. Unlike lead, bismuth is actually quite brittle, and it also has a fairly low melting point.
Brittle? That's interesting for a heavy metal. So what's it used for?
Well, one significant use is in low-melting alloys and solders, often as a non-toxic replacement for lead. That's a big plus these days.
Ah, the lead-free solder often uses bismuth.
Often, yes. You'll also find it in pharmaceuticals. Maybe the most common example is bismuth subsalicylate, the active ingredient in things like Pepto-Bismol for upset stomachs.
No way. That's bismuth.
That's bismuth. And perhaps surprisingly, it pops up in some cosmetics too.
Cosmetics. What does it do there?
Bismuth compounds, like bismuth oxychloride, can give cosmetics a pearlescent, shimmery effect. That subtle glow. It's all about how it reflects light.
Huh. From stomach remedies to makeup shimmer, who knew?
And here's a really weird property. Bismuth actually expands slightly when it freezes, when it solidifies. Most metals shrink.
It expands. That is unusual. Like water turning to ice. Okay, quite a character, bismuth. Let's switch gears now, maybe move to a different part of the periodic table. How about cerium?
Cerium, Ceri number 58. Now we're entering the lanthanide series, the rare earth elements, though cerium itself isn't actually that rare.
Okay, lanthanides. What's special about cerium?
A key thing is its chemical versatility. It's quite reactive, and it can exist in different oxidation states, meaning it can gain or lose different numbers of electrons easily. That makes it flexible in chemical reactions.
Chemically flexible. So what does that allow it to do in practice?
Well, that flexibility is key. Cerium is a component in something called mish metal. It's a pyrophoric alloy.
Pyrophoric, meaning
It ignites spontaneously in air when scratched or struck. Think of the flint in a lighter. That often contains mish metal, including cerium.
lighter flints. Okay, got it.
Exactly. And a very different but hugely important application is in catalytic converters in cars. Cerium compounds help catalysts convert harmful exhaust gases like carbon monoxide into less harmful substances.
Wow, from making sparks to cleaning up car exhaust. That's quite a range. Anything else?
Yes, it's also used in polishing compounds, especially for glass and high-precision optics. It helps create those ultra-smooth, clear surfaces on lenses and screens. And cerium compounds can be added to specialized glasses and ceramics to give them specific properties, like absorbing UV light.
So the spark in our lighters, the clean air from our cars, the clarity of our phone screens, cerium's quietly involved in a lot. Okay, let's talk about one that's definitely not quiet, an element everyone knows.
Gold.
Gold. Element 79. It really does hold a special place, doesn't it? Because of its history, its rarity, its undeniable value. Civilizations have been captivated by it for millennia. Absolutely. It's the symbol of wealth, beauty, permanence. But beyond just looking good, what makes it special scientifically?
Well, probably its most outstanding property is its incredible resistance to corrosion and tarnish. Gold just doesn't rust or degrade easily when exposed to air, water, or most acids.
Why is that?
It's down to its electron configuration. It's very stable, making it chemically quite unreactive. That's why ancient gold artifacts can survive for thousands of years and still look brilliant.
That explains its long history in jewelry and coinage. It lasts, physically and, well, economically too.
Precisely. Its role as a store of value is deeply tied to that permanence. But beyond finance and jewelry, gold is also important in electronics.
Electronics, because it conducts electricity well.
Yes, it's an excellent conductor, but crucially, it also resists corrosion. In sensitive electronic components, even a tiny bit of tarnish on a contact point can cause failure. Gold reliability makes it essential for connectors, switch contacts, bonding wires, and microchips.
So it's not just bling. It's about rock-solid performance in demanding tech. What about other uses? I think I've heard of gold in medicine.
You have. Gold has uses in dentistry for fillings, crowns, because it's biocompatible, durable, and doesn't corrode in the mouth. And there are some specialized medical applications, like in certain injectable treatments for arthritis, although that's less common now, and sometimes in nanotechnology for diagnostics or drug delivery.
Amazing. One element holding so much cultural significance in having these high-tech and medical uses, where does it actually come from? How does gold form?
Gold deposits typically form through geological processes involving superheated water, hydrothermal fluids circulating deep within the Earth's crust. These fluids dissolve tiny amounts of gold from the rocks they pass through.
And then?
Then as conditions change, temperature, pressure, chemistry, the gold precipitates out of the fluid, often along with quartz forming veins in the rock. Or sometimes it's dispersed in tiny particles throughout a larger rock mass.
And getting it out. Mining, obviously, but what else?
Mining, yes. Then extraction usually involves crushing the ore and using chemical processes to dissolve the gold. The most common method uses cyanide solutions, which selectively dissolve gold, allowing it to be separated from the rock. Then further refining gets you the pure metal.
Fascinating. From deep underground fluids to refined bars and tiny electronic components. Quite a journey. Okay, let's swing to the complete opposite end of the scale now. The simplest, lightest, most abundant element in the entire universe. Hydrogen.
Hydrogen. H element number 1. It truly is fundamental. The simplest atom. Just one proton, usually one electron. It's the original stuff, the building block for almost everything else in the cosmos, through stellar nucleosynthesis.
The most abundant in the universe. It's hard to even picture that scale. And it packs a punch, right? Yeah. High energy content. Fuel potential.
Absolutely. Hydrogen has a very high energy density by weight. That's why it's used as a rocket fuel, powerful and lightweight. When it burns with oxygen, the main byproduct is just water, which is why it's often touted as a clean fuel.
Powering rockets with just hydrogen and oxygen, producing water. There's an elegance to that.
Yeah.
What about here on Earth? Industrial uses
Oh, it's vital in many industrial processes. A huge one is the Haber-Bosch process.
for making ammonia.
Exactly. Using hydrogen and nitrogen from the air to make ammonia for fertilizers. That process arguably feeds a huge portion of the world's population. Hydrogen is also used in refining petroleum and in hydrogenation, like turning liquid vegetable oils into solid or semi-solid fats, like margarine.
So essential for space travel and putting food on the table? Amazing. I also remember there are different kinds of hydrogen, isotopes.
Yes, that's right. The most common form, just one proton, is called protium. Then there's deuterium, which has a proton and a neutron, sometimes called heavy hydrogen.
Deuterium, right. Used in heavy water for some nuclear reactors.
Correct. And then there's tritium, with one proton and two neutrons. Tritium is radioactive and much rarer. These isotopes are really important in nuclear physics and fusion research.
Fusion power hopes rely on deuterium and tritium, don't they?
They do, aiming to fuse them together to release energy. Another interesting thing is occluded hydrogen.
Occluded? What's that?
Some metals, like palladium, have this amazing ability to absorb huge volumes of hydrogen gas into their metallic structure, almost like a sponge. This has potential applications for hydrogen storage.
Metals acting like hydrogen sponges. Neat idea.
And wasn't there something about different molecular forms of hydrogen, too?
Ah, yes, ortho and parahydrogen. This relates to the relative spin directions of the two protons in the H2 molecule. They have slightly different physical properties, especially at low temperatures. It's scientifically interesting, but doesn't usually impact everyday use as much.
Layers upon layers, even for the simplest element. What about hydrogen just floating around in our atmosphere?
It's there, but only in very tiny amounts. Being so light, it tends to escape Earth's gravity over time, but it does participate in atmospheric chemistry.
Okay. And maybe the most crucial role for hydrogen on Earth: water. Absolutely fundamental. The hydrogen atoms in water molecules form hydrogen bonds, those relatively weak attractions between molecules. These bonds are responsible for almost all of water's unique life-sustaining properties: its high boiling point, its ability to dissolve so many things, its role in biological structures. Life as we know it depends on hydrogen bonding.
Wow. Hydrogen. Tiny atom. Massive impact. Okay, let's talk about another light gas, number 2 on the table. Helium.
Helium, you bet. Element 2. A noble gas, meaning it's extremely unreactive, chemically very stable, very inert.
Noble and aloof, but has some really unique physical properties, right? Super cold.
Incredibly so. Helium has the lowest boiling point of any element, just 4.2 Kelvin, which is about minus 269 degrees Celsius, or minus 452 Fahrenheit, or barely above absolute zero.
Mind-bogglingly cold. What do we use that extreme cold for?
That makes it the ultimate coolant for cryogenics. It's essential for cooling the superconducting magnets in MRI machines.
Ah, MRI magnets need helium.
They do, and also in particle accelerators and lots of low-temperature physics research. Beyond the cold, it's famous for being lighter than air and non-flammable, making it the safe choice for filling balloons and airships.
Much safer than the Hindenburg's hydrogen, definitely.
Definitely, and it's also used in breathing mixtures for deep-sea divers. Replacing nitrogen with helium helps prevent nitrogen narcosis, or the bends, at high pressures.
So high-tech magnets, party balloons, deep-sea diving, quite a mix. Where does helium come from? Is it made?
Well, ultimately, it's made in stars through nuclear fusion, fusing hydrogen atoms together. That's where most of the universe's helium comes from.
Okay, but the helium we use here on Earth.
The helium we extract here on Earth actually comes from the radioactive decay of heavy elements like uranium and thorium, trapped deep underground within natural gas deposits. Alpha particles released during decay are essentially helium nuclei. They pick up electrons and become helium atoms, accumulating over millions of years.
So it's a byproduct of natural radioactivity, trapped with natural gas. Fascinating. And being a noble gas, it really doesn't react much.
Hardly at all. Its outer electron shell is completely full, making it extremely stable and chemically inert. Only under very extreme conditions can it be forced into forming unstable compounds.
And while it's the second most common element in the universe after hydrogen, it's actually quite rare here on Earth, isn't it? There are concerns about supply.
That's a major point, yes. While abundant out there, it's relatively scarce in our atmosphere because, like hydrogen, it's so light it escapes Earth's gravity. The helium we use is a finite resource trapped underground, and depleting those reserves is a growing concern, especially given its critical uses in science and medicine.
Definitely something to think about.
Yeah.
Okay, let's move on to another light element, number 3.
Lithium.
Lithium. Light element 3. The first of the alkali metals we're discussing. Like others in its group, it's highly reactive, having just one electron in its outer shell that it's very eager to give away. Alkali metals are always keen to react. And lithium is super light, right? The lightest metal.
It is. The least dense of all solid elements under normal conditions. It can actually float on oil.
Floats on oil. Okay. So light and reactive sounds like a recipe for batteries.
Exactly. That combination is perfect for batteries, especially lithium-ion batteries. Their high energy density and lightweight have revolutionized portable electronics, phones, laptops.
Everything, basically.
Pretty much everything. And now they're absolutely crucial for electric vehicles, driving that whole industry forward.
Lithium-ion batteries really have changed the game in the last few decades. Any other major uses for lithium?
Well, historically, a less peaceful application was in thermonuclear weapons specifically, lithium deuteride was used.
That's right.
In more constructive uses, it's added to some alloys, particularly aluminum alloys, to increase their strength and reduce their weight. That's very valuable in aerospace for making lighter, more fuel-efficient aircraft.
Lighter planes, that makes sense.
Mm-hmm.
And isn't there a medical connection too? Mood disorders.
Yes, that's right. Lithium compounds, specifically lithium carbonate, are used as mood stabilizers in psychiatry, particularly for treating bipolar disorder. The exact mechanism isn't fully understood, but it's been a very effective treatment for many people for decades.
Wow. From phone batteries to airplane parts to mental health treatment, lithium's impact is incredibly diverse. Okay, next element, number 4, beryllium.
Beryllium, B. Number 4. Now we're in group 2, the alkaline earth metals. Beryllium stands out for being exceptionally lightweight, but also remarkably stiff and strong for its weight. It also has a high melting point.
Lightweight, stiff, and strong. Sounds like high-performance material territory.
It absolutely is. Its primary use is in alloys, especially beryllium copper. This alloy combines high strength, hardness, good conductivity, and importantly, it's non-sparking.
Non-sparking, why is that important?
Think about tools used in environments where flammable gases or dust might be present, like oil rigs or chemical plants. A spark from a regular steel tool could be disastrous. Beryllium copper tools provide that safety margin. It's also used in aerospace, for high-precision instruments, gyroscopes, things where stiffness and stability are critical.
Got it. Safety tools and precision instruments. What else? Any nuclear roles?
Yes. Beryllium is used in nuclear reactors as a neutron reflector or moderator. It helps manage the neutron population to sustain the chain reaction efficiently. However...
There's always a however with these interesting elements, isn't there?
Often, yes. Beryllium and its compounds, particularly inhaled dust, are highly toxic and carcinogenic. Handling it requires extremely strict safety controls. Berylliosis is a serious lung disease caused by beryllium exposure.
Right, so another powerful element that demands respect and careful handling. Okay, element number 5, bridging the gap between metals and nonmetals. Boron.
Boron would be number 5. A metalloid, having properties of both metals and nonmetals. Its chemistry is fascinating, largely due to its electron structure. It only has 3 outer electrons, leading to unique bonding behavior. It loves to form strong covalent bonds, sharing electrons.
Strong covalent bonds. Does that lead to hard materials?
It can. But maybe its most famous application comes from how it modifies glass. Boron is key to borosilicate glass.
Like Pyrex.
Exactly like Pyrex. Adding boron oxide to glass drastically reduces its thermal expansion. That means it can handle sudden temperature changes without shattering, going from hot oven to countertop, for example. That's why it's used for lab glassware and cookware.
The unsung hero of the kitchen and the lab. What other forms does boron take?
Well, elemental boron itself is very hard and has a high melting point. Boron fibers are used to reinforce composite materials, making them incredibly strong and lightweight. Think high-performance aerospace parts or sporting goods.
Like fancy golf clubs or tennis rackets.
Could be, yes. On a more fundamental level, boron is an essential micronutrient for plants. And many people know it through borax, a boron compound used as a cleaning agent and laundry booster for ages.
Plants need it. We clean with it.
Okay.
It's quite versatile. What about compounds with hydrogen? Boranes.
Yes, the boranes, or boron hydrides, are a whole class of compounds with unusual structures and bonding. Some are highly reactive and were even studied as potential high-energy rocket fuels, though that didn't really pan out commercially. They are important reagents in organic chemistry, though. And some boron compounds, like cubic boron nitride, are extremely hard, almost as hard as diamond.
Nearly as hard as diamond.
Diamond metalloid.
Okay, let's move to the absolute cornerstone of life as we know it,
Yeah.
carbon.
Carbon. See, element number 6. Where do you even begin? It's the fundamental element of organic chemistry, forming the backbone of virtually all biological molecules. Its ability to form 4 strong covalent bonds, including long chains and rings with itself and other elements, allows for the incredible complexity of life.
We are literally carbon-based life forms. And it exists in such different forms too, doesn't it? Allotropes.
Exactly. Carbon's allotropes are famous. There's diamond, the hardest known natural substance where each carbon atom is bonded tetrahedrally to 4 others in a rigid lattice.
Super hard, super valuable.
Then there's graphite, which is soft, gray, and conducts electricity. Here, the carbon atoms are arranged in flat hexagonal sheets that can easily slide over each other. That's why it's used as a lubricant and in pencil lead.
Complete opposites, diamond and graphite, yet both pure carbon.
And that's not all. We now know about fullerenes like buckyballs, C60 molecules shaped like soccer balls, and carbon nanotubes, tiny cylinders of graphite sheets with amazing strength and electrical properties. Graphene, a single sheet of graphite, is another one with huge potential.
So many forms. And carbon is also central to our energy, isn't it? Fuels.
Absolutely. Fossil fuels, coal, oil, natural gas are primarily hydrocarbons, compounds of carbon and hydrogen.
Yep.
Burning them releases energy, powering much of our world. Carbon is also essential in steelmaking. Adding a small amount of carbon to iron makes it much harder and stronger, creating steel.
Fuel, steel. What else? Carbides.
Yes, carbon forms carbides with many metals. These are often very hard refractory materials used in cutting tools or high-temperature applications. Think tungsten carbide or silicon carbide. And of course, back to biology, carbohydrates, fats, proteins, DNA, RNA, all intricate carbon structures.
It's just fundamental to life, to industry, to everything.
Yep.
Hey, next door neighbor, element 7, nitrogen.
Nitrogen. And element 7, the most abundant gas in our atmosphere, making up about 78% of the air we breathe. Its most notable chemical feature is the N2 molecule itself.
The molecule in the air.
Yes. 2 nitrogen atoms joined by an incredibly strong triple bond. This triple bond makes N2 very stable and relatively unreactive or inert under normal conditions. It takes a lot of energy to break it.
So mostly hanging out and not reacting, but it's still vital for life, isn't it? Proteins, DNA.
Absolutely vital. Despite the inertness of atmospheric N2, nitrogen atoms are essential components of all amino acids, which build proteins, and nucleic acids, DNA and RNA, which store and transmit genetic information. Life can't exist without nitrogen compounds.
So how does life get hold of it if the N2 in the air is so unreactive?
That's the crucial process of nitrogen fixation. It's the conversion of atmospheric N2 into usable forms like ammonia, NH3, or nitrates, NO3.
Wow.
Certain bacteria, some living freely in soil, others in nodules on the roots of legume plants like beans and peas, can do this naturally.
Bacteria are the key.
They are for the natural cycle. Lightning strikes also fix some nitrogen, but industrially, the Haber-Bosch process is massive. It uses high temperature and pressure with a catalyst to combine nitrogen from the air with hydrogen to make ammonia, primarily for fertilizers.
The Haber-Bosch process, feeding the world again, alongside hydrogen.
A huge impact. Besides fertilizers, nitrogen compounds are also the basis for many explosives like TNT or nitroglycerin. And pure nitrogen, especially in liquid form, liquid nitrogen, is used as a cryogen for freezing things quickly or maintaining very low temperatures.
Wasn't there something about deep-sea diving again? Nitrogen narcosis.
Yes. At high pressures underwater, more nitrogen dissolves in the bloodstream, which can impair judgment and coordination, sometimes called rapture of the deep. That's why divers sometimes use helium mixtures instead.
Fascinating. Life giver, explosive component, deep-sea hazard. Quite the personality. Okay, element 8, the one we can't live without for more than a few minutes. Oxygen.
Oxygen. Oh, element 8. Essential for respiration for almost all animals and for combustion fire. It makes up about 21% of our atmosphere, mostly as the diatomic molecule O2. And unlike nitrogen, oxygen is quite reactive.
That reactivity is key, right?
Well,
for getting energy.
Exactly. Oxygen is a powerful oxidizing agent. Oxidation is the process where a substance loses electrons, often by combining with oxygen. In respiration, our bodies slowly oxidize food molecules, releasing the energy stored in them in a controlled way. Combustion is just a much faster, uncontrolled oxidation, releasing energy as heat and light.
So breathing and burning are fundamentally related through oxygen's reactivity. And where does all this atmospheric oxygen come from?
Primarily from photosynthesis. Plants, algae, and cyanobacteria use sunlight, water, and carbon dioxide to create their own food, sugars, and they release oxygen as a byproduct. It's a beautiful planetary balance.
Plants making the air we breathe.
Huh.
Amazing. Is there another form of oxygen? Ozone?
Yes, ozone, O3, is an allotrope of oxygen, with 3 oxygen atoms bonded together instead of 2. While ozone near the ground is a pollutant, the ozone layer high up in the stratosphere is crucial.
Why is that?
It absorbs most of the harmful high-energy ultraviolet, UVB and UVC radiation from the sun, protecting life on the surface from damage. It's like Earth's natural sunscreen.
A vital shield. Who first figured out oxygen was a thing?
Its discovery is usually credited to Carl Wilhelm Scheele in Sweden and Joseph Priestley in England, working independently around the 1770s. They both isolated it and recognized it as a distinct component of air necessary for combustion and respiration.
A fundamental discovery. Okay, let's move to element 9, known for being extremely enthusiastic. Fluorine.
Fluorine, F element 9. You could say enthusiastic. It's the most electronegative element there is.
Most electronegative, meaning it really wants electrons.
It wants electrons more than any other element. It pulls them very strongly towards itself in chemical bonds. This makes elemental fluorine, F2, incredibly reactive, maybe the most reactive of all elements. It reacts often violently with almost everything, even some noble gases under certain conditions.
Wow. Handled with extreme care then. What do we use something so reactive for?
Well, precisely because it forms such strong bonds, its compounds can be very stable and useful. Think fluorocarbons. Teflon, polytetrafluoroethylene, or PTFE, is famous the non-stick coating. It's incredibly inert because the carbon-fluorine bonds are so strong.
Teflon. So fluorine's reactivity leads to stability in its compounds. Makes sense. What else?
Older refrigerants, the CFCs, chlorofluorocarbons, or freons, were fluorine compounds. Effective but damaging to the ozone layer, so they've been largely phased out. And of course, fluoride in toothpaste and drinking water.
Fluoride for teeth, right. How does that work?
Fluoride ions get incorporated into tooth enamel, making it harder and more resistant to acid attack from bacteria, thus preventing cavities. Small amounts have a big protective effect.
From nonstick pans to healthy teeth. Was it hard to isolate pure fluorine in the first place, given its reactivity?
Extremely hard. It attacked containers, electrodes, everything researchers tried. It took decades of effort. Finally, in 1886, the French chemist Henri Moissan succeeded using electrolysis of a potassium fluoride solution in anhydrous hydrogen fluoride at very low temperatures. He won a Nobel Prize for it. And hydrogen fluoride itself, HF, while technically a weak acid, is dangerously corrosive, famously known for etching glass.
Definitely an element that commands respect. Okay, let's move back to the noble gases. We've done helium and neon. How about argon?
Argon, our element 18, another noble gas, so chemically very inert. It's actually the most abundant noble gas in Earth's atmosphere, making up nearly 1%, much more common than neon or helium in the air.
1%. That's surprisingly high for a noble gas. Why so much argon?
Most of it is argon-40, which is produced by the radioactive decay of potassium-40, a naturally occurring isotope found in rocks in the Earth's crust. It slowly seeps out and accumulates in the atmosphere over geological time.
Radioactive decay again. So what do we use all this unreactive argon for?
Its inertness is its main selling point. It's used to provide an unreactive atmosphere in various situations. For example, in welding, especially TIG welding, argon gas shields the hot metal from reacting with oxygen or nitrogen in the air, which would weaken the weld.
Like a protective blanket during welding. Makes sense.
Exactly. It's also used to fill incandescent light bulbs. The argon atmosphere slows down the evaporation of the hot tungsten filament, making the bulb last longer. And it's used in the production of highly reactive metals like titanium, again, to prevent unwanted reactions during processing. Some lasers also use argon.
So basically, whenever you need to keep air away from something sensitive or hot.
That's a good way to put it. And how was it discovered? It was actually the first noble gas to be found in air.
Oh, really? Before helium or neon?
Yes. In 1894, Lord Rayleigh and Sir William Ramsay noticed that nitrogen extracted from the air was slightly denser than nitrogen produced chemically. They hypothesized there was an unknown, heavier gas mixed in with the atmospheric nitrogen, and they managed to isolate it argon, meaning the lazy one, or the inactive one in Greek, because of its lack of reactivity.
A tiny density difference led to a whole new element. That's brilliant. Okay, let's quickly cover the other noble gas famous for lights. Neon.
Neon, element 10, another noble gas discovered by Ramsay and Travers shortly after argon. Its defining characteristic, the one everyone knows, is that brilliant, intense reddish-orange glow it produces when an electric current passes through it in a vacuum tube.
Neon signs. Instantly recognizable. Is that its main use?
Pretty much the dominant use, yes, that iconic lighting. It's also used in some specialized applications like high-voltage indicators, lightning arresters, and certain types of lasers. Helium neon lasers were very common. It can be used as a cryogenic refrigerant too, but it's less common and more expensive than liquid nitrogen and doesn't get as cold as helium.
So mostly about the glow. Where does it come from? Is it common?
It's present in the atmosphere, but in much, much smaller amounts than argon, only about 18 parts per million. Like other noble gases, it's obtained by fractional distillation of liquefied air. Its name comes from the Greek neos, meaning new.
A new gas that lit up the 20th century. Okay, let's jump back to the alkali metals.
Sodium.
Sodium, element 11. A classic alkali metal, soft, silvery white, and extremely reactive. You'll never find pure sodium metal in nature.
Because it reacts so easily with water, air.
Vigorously with both. It tarnishes instantly in air and reacts explosively with water, producing hydrogen gas and sodium hydroxide. It has to be stored under oil or in an inert atmosphere. But its compounds are incredibly abundant, especially sodium chloride, NaCl, common table salt, found in seawater and vast underground deposits.
Salt everywhere. Essential for life too, isn't it? Nerves, muscles.
Absolutely crucial. Sodium ions, Ni+, are vital for nerve impulse transmission, muscle contraction, and maintaining the fluid balance in our bodies. We need sodium compounds in our diet. So essential in compound form, dangerous in pure form. What are the uses for the pure metal?
Because it's so reactive, it's used as a strong reducing agent in some chemical syntheses. Historically, it was important for making tetraethyl lead, the anti-knock additive in gasoline, but that's phased out. It's used to produce other reactive metals like titanium or zirconium, and sodium vapor lamps, those lamps giving off that characteristic yellow-orange light often used for street lighting, contain sodium metal vapor.
Ah, those yellow street lights, that's sodium. Okay, let's do its neighbor in group 2, magnesium.
Magnesium, Mg element 12, an alkaline earth metal like beryllium, but much more common and less toxic. It's also very lightweight and reasonably strong, especially when alloyed.
Lightweight and strong sounds familiar. Alloys again.
Yes, magnesium alloys, often with aluminum, zinc, or other elements, are prized for their high strength-to-weight ratio. They're used where lightweight is critical aerospace components, car parts like engine blocks or wheels, portable electronics casings, power tools.
Trying to make things lighter.
Exactly. Magnesium is also famously flammable, burning with a brilliant, intense white light. That's why it's used in flares, fireworks, and incendiary devices. Older camera flash bulbs used magnesium foil.
That bright white flash.
Right.
And it's important biologically, too, isn't it? Plants.
Hugely important. Magnesium is the central atom in the chlorophyll molecule, the green pigment that captures sunlight for photosynthesis. No magnesium, no photosynthesis as we know it. In animals, magnesium ions are essential for hundreds of enzyme functions, muscle and nerve function, maintaining heart rhythm. It's a vital mineral.
Wow. Central to capturing the sun's energy and keeping our bodies working. Magnesium's pretty key. Okay, let's talk about the most abundant metal in the Earth's crust, aluminum.
Aluminum. Ow. Element 13, ubiquitous. Lightweight, strong, resistant to corrosion, good conductor of electricity and heat, non-toxic, easily recyclable. It has a fantastic combination of properties.
We see it everywhere. Cans, foil, window frames, airplanes, power lines. How do we get so much of it? From what ore?
It mainly comes from bauxite ore, which is rich in aluminum oxides and hydroxides. Extracting the aluminum is a two-stage process. First, the Bayer process purifies the aluminum oxides, alumina, from the bauxite.
Okay, get pure alumina.
Then, the Hall-Héroult process uses electrolysis to break down the alumina into molten aluminum metal and oxygen. This step requires huge amounts of electricity, which is the main cost and environmental footprint of aluminum production.
Energy intensive, but worth it for the metal's properties. What are some standout applications besides the everyday ones?
Well, its use in transportation is massive. Aerospace has relied on aluminum alloys for decades for their lightness and strength. Cars are using more and more aluminum to reduce weight and improve fuel efficiency. High-voltage electrical transmission lines often use aluminum conductors, sometimes reinforced with steel, because aluminum is much lighter than copper for similar conductivity, reducing the need for support towers.
Lighter power lines, interesting. Any specialized forms?
Yes, there are advanced aluminum alloys and composites. For example, SAP-sintered aluminum powder is aluminum powder that's pressed and heated. It retains its strength remarkably well at high temperatures, better than regular aluminum alloys, making it useful in demanding aerospace applications.
Always pushing the boundaries. Okay, we've covered a lot of ground. Let's finish with the heavy radioactive elements mentioned in your sources. Uranium, neptunium, and plutonium.
Right, uranium, U-element 92. A naturally occurring radioactive element, the heaviest naturally abundant one. Its main significance today comes from the isotope uranium-235.
The fissile one.
Exactly. U-235 is fissile, meaning its nucleus can be split when hit by a neutron, releasing a large amount of energy and more neutrons. This is the basis for nuclear fission reactors generating electricity, and also for nuclear weapons. Natural uranium is mostly U-238, which isn't easily fissile, so uranium often needs to be enriched to increase the percentage of U-235 for use in reactors or weapons.
So uranium is the primary fuel for nuclear power and weapons. What about the next two elements, neptunium and plutonium? They're man-made, right?
Primarily, yes. Neptunium, NP element 93, and plutonium, Pu element 94, are transuranic elements heavier than uranium. They were first synthesized in the 1940s. Neptunium is formed in nuclear reactors when uranium-238 absorbs a neutron, and then it decays into plutonium.
So plutonium comes from uranium in reactors.
The most important isotope, plutonium-239, is formed that way, and Pu-239 is fissile, like U-235. In fact, it's a major nuclear fuel itself, produced and consumed in most reactors, and it's also the primary fissile material used in many nuclear weapons. Your sources apparently go into some detail on plutonium's discovery, its isotopes, and its role in early atomic projects.
Different elements that represent a very powerful and very complex side of science and human history.
They certainly do. And looking back at everything we've discussed, from hydrogen, the simplest building block, to these complex, heavy elements, the diversity is just incredible.
It really is. From the lightest gases holding stars together, to the metals building our cities and technologies, to the elements essential for life itself.
And how even familiar elements, ones we think we know, have these hidden depths, these tangled histories of discovery, use, and sometimes misuse, just as your sources highlighted.
It definitely makes you appreciate the fundamental nature of chemistry and material science.
Absolutely. It leaves you thinking, doesn't it? How our understanding and our ability to manipulate these basic building blocks keeps evolving. It opens up amazing new possibilities, but also presents us with some really significant challenges for the future.
A perfect thought to end on. Consider the elements around you. Maybe pick one and do your own deep dive. There's always more to discover. Thanks for joining us.